Imagine standing on a mountain, completely surrounded by fog. You cannot see the whole landscape. You cannot see where the valley is. All you can feel is the slope beneath your feet, whether the ground tilts upward or downward, left or right. Your goal: reach the lowest point. Your only tool: the slope of the ground where you stand. This single problem, finding the minimum of an unknown landscape, is the core challenge of machine learning optimization. And the elegant solution discovered decades ago still powers every AI system running today. In machine learning, that mountain becomes a loss function. Replace the terrain with a mathematical surface, where height represents how wrong your model's predictions are. Up here, enormous error. Down here at the bottom, near-perfect predictions. The simplest loss function is f of x equals x squared. Clean, symmetric parabola. Every position on this curve represents a different parameter setting. Move left, error changes. Move right, error changes. Your job: find the exact x that minimizes this function. That is the parameter where your model makes the fewest mistakes. So how do we navigate without seeing the full landscape? We use the gradient. At any point on the curve, draw the tangent line. That line's slope is the gradient. If the slope is positive, we're to the right of the minimum. We should move left. If the slope is negative, we're to the left of the minimum. We should move right. The gradient always points uphill, in the direction the function increases fastest. To minimize, we simply move in the opposite direction. This single insight is the mathematical foundation of gradient descent. Let's derive the update rule precisely. Our loss function is j of x equals x squared. The derivative, the gradient, is 2x. At position x equals 3, the gradient is 6. The surface rises steeply to the right, so we step left. Subtract the gradient, scaled by eta. New x equals old x minus eta times 2x. Eta is a small positive number, the learning rate. It controls the step size. We apply this update repeatedly at every step. In the general case, any loss function, any parameter vector, the rule becomes theta new equals theta old minus eta times the gradient of j with respect to theta. This equation is the engine of all modern machine learning, from the simplest linear regression to the largest language models ever built. The learning rate eta controls how large each step is, and choosing it correctly is critical. Too small. Each update barely moves the parameter. The model does learn, but painfully slowly, taking thousands of extra iterations to converge. Too large. Each step overshoots the minimum entirely. The algorithm bounces back and forth across the valley, or diverges completely, never converging. The optimal learning rate takes confident, measured steps, descending efficiently toward the minimum without overshooting. Finding the right learning rate is part mathematics, part art, and it is one of the most consequential decisions in any machine learning project. Real neural networks don't minimize a single parabola. Their loss landscapes are high-dimensional surfaces of extraordinary complexity, full of valleys, plateaus, saddle points, and local minima. A local minimum looks like the bottom of the world from nearby, but the true global minimum may be far away. Modern optimizers like Atom and RMSprop add momentum and adaptive step sizes to navigate these complex terrains more reliably. But at their core, every one of them follows the same principle. Measure the gradient, step downhill, repeat. Every neural network ever trained uses gradient descent. Forward pass computes the prediction. Loss measures the error. Backpropagation computes the gradients layer by layer. Gradient descent updates every weight. Repeat millions of times, and the model learns. Gradient descent is not just an algorithm. It is the reason machines can learn at all.